Alright, welcome back. So we got some good news. Last video we tried to get an inter-AS LSP working, but unfortunately what I learned is that in order to do that, so much like with BGP where you've got to share your routes, you've got to export them out and advertise them, and then all of these learn the routes through BGP. You've got to do the same thing to have a LSP come up inter-AS, but instead of sharing routes, you're going to share the link state database. And from what I read, you can't share a link state database between different kinds of IGPs. So I could not take the link state database from OSPF and load it into ISIS. I could only do that if this were also OSPF. So that's a huge, I think worth a giant downvote, but unfortunately I'm kind of I think behind, so I just want to move on and get through as much material as I can. So I marked this done. 6 videos is kind of a bit much, so we're going to move on to IGP-BGP within the context of traffic engineering for Mpls. So I'm not exactly sure what that means, but we will find out shortly. Okay, and if you will excuse me for a second here. There we go. Okay, so let's keep going on this. We're going to start the same way we start with everyone. And lately, actually, that has been verifying that I uploaded it to YouTube. I just kind of been having trouble remembering that because I'm doing like multiple things now. So let's have a look. And so we'll go to my channel here. And yep, so this is the 6th video. So look at my notes. I'm pretty sure there were 6. There might have been 7, but I think, yeah, I remember when I did this yesterday. So yep, that's the 6th video. Oops, let's leave that up though, so we can get our tags and our titles ready to go for the next one. There we go, and then I'll go back to here so that that is listed there. So we can get rid of the Rsvp tag. It's no longer going to be TED. It's going to be IGP-BGP, but it's still going to be within the context of Mpls and traffic engineering. Okay, so we can add a BGP tag. I think that's a good one to have on there. A lot of people, I think, are interested by BGP and networking just because of how impactful it is. So, yep, this should be good. We'll also probably be able to add, let's just do that right now. Let's add OSPF and let's add IS dash IS. Let's not add ISIS because we might get bad associations with that tag. So I think some of my other videos might have had it without the dash, but for this one, let's just call it what it actually is in the context of network engineering. In the context of network engineering, it does have a dash because it's intermediate system to intermediate system. So if I do a Google search for IS-IS, let's do an experiment here. So we're gonna go capital IS dash capital IS. So yep, we've got a lot of things that aren't related to network engineering, but we do have a result right here that is as related as you could possibly get. It's actually the RFC for ISIS. Now let's see what I get if I don't include a dash. Yep, so you see if I don't include that dash, I don't get that RFC. So for both searches, we get a lot of results that are not related to what we want to focus on. But for this search, we actually do get two results on the first page that are exactly what we're looking for. So I'm going to keep that dash in there. So let's keep moving on. And let's go and do the number one thing I like to do when learning about a new topic for this exam, and that's head right to the Juniper command line interface, and then directly to the help apropos, because I get to use that during the test. Okay, so let's try it with capital letters. Okay, so still no hits. Let's try traffic engineering, or let's just try traffic. Okay, so we do have yep, so unfortunately it looks like they listed it in the opposite order. When we list it with BGP first, we do have an exact match. So I'm just going to do that so that that's something I never even thought to do. I think I'll be doing that from now on if I've got something like this, just seeing what comes up if I put it in the reverse order. So yep, we've got two different things. So I'm going to start with this one, and I'll make it all on one screen. Okay, so this is using Rsvp and LDP routes for traffic forwarding. I'm going to take a quick break. I'll come back and we'll read that article. All right, I'm back. Configure the BGP-IGP option of the traffic engineering statement to cause BGP and the interior gateway protocols, IGPs, to use LSPs for forwarding traffic destined for egress routers. The BGP-IGP option causes all INET.3 routes to be moved to the INET.0 routing table. In the ingress router, include the traffic engineering BGP-IGP statement. Traffic engineering BGP-IGP, you can include the statement at the following hierarchy levels: edit protocols Mpls, edit logical system name protocols Mpls. Note the BGP-IGP option of the traffic engineering statement cannot be configured for virtual private networks, VPNs. VPN routing instances require that routes be in the INET.3 routing table. Alright, so let's take a look at the INET. And hitting the pause button did nothing, so I'm going to hit it again. Alright, I am back. I noticed that this video is only 8 minutes long. I'm kind of surprised by that. But let's just keep going. So, Junos routers, what does the INET3 table actually do? Hi pals, today in this two-part blog post, I'm going to take you on a magical journey. And by take you on a magical journey, I mean teach you what the INET.3 table does and how to manipulate the way Juniper routers resolve next hops in BGP/MPLS networks, which is basically the same thing as a magical journey, right? In this first post, we're going to talk about exactly what an LSP is, what INET.0 and INET.3 do. Oh, okay, well, there's two parts. and the situations where we do and don't use them. So I'll add this to my notes before continuing on. We'll talk about why we might want to copy them instead of moving them. We'll talk about how to advertise LSPs as links in your IGP. And we'll even talk about how to use LSPs to forward all traffic without it affecting your network in unintended ways. Until today, all of these concepts were merely the stuff of dreams. Well, Lucy, today your dreams are over. Who's Lucy? Alright, so I'm kind of tempted to set this up in my own lab, but let's just do what he says and imagine it. So imagine a network like the one in this diagram, or better yet, don't imagine it at all, and instead just look at the diagram with your eyes. Save your imagination for imagining better things, like whether a dragon could ever learn to touch type. I would say no. Or whether Ban Ki-moon has ever watched Shrek. I don't know who this is. It's a South Korean politician. I would say no, he hasn't watched Shrek, but I think he might have played the game Go. I would put some money on that. But watching Shrek, I would say probably not. Now you might know about inet.0 already. It is the normal routing table. By default, static and directly connected routes all go into this table, as do prefixes learned by an interior gateway protocol, IGP, like OSPF or ISIS. And on the whole, when we learn prefixes via an IGP, the next hop to those IPs will be the larger, giving us the will be the router giving us the advertisement. For example, in our diagram, if router 2 advertises to router 1, router 1's next hop will be 10.10.12.2 out to the directly connected interface to router 2. Routes learnt by BGP also go into the inet.0 table, but next hops in BGP work a little differently. You see the two routers at either end of a network might have an IBGP relationship, but even though there's many other routers in between them, the IBGP routers still advertise themselves as the next hop for any prefix they advertise. Or sometimes they don't even do that. It's possible that they'll advertise a next hop of the router that they themselves learned it from. Either way, this means that the router receiving the routers, I think you meant to say routes here, needs to then do a second lookup to work out the actual next hop to resolve this far away next hop. Here's an example. In our network, every router has an IBGP peering to every other router. Let's concentrate on router 1 again, which has an IBGP peering to router 3. So what's going to happen is the next hop is going to be an address from router 1, which router 3 can't use as a next hop because it's more than one hop away. R3 is advertising 69.69.69.0/24. Oh god, nice. To R1 with R3. Oh, because it's. I was about to say, why can't it why can't there be 4 of them? But it's because he's using a /24. I mean, he could use a slash. No, there's no way to get a 4th one. With R3 specifically, it's loopback 3.3.3.3 as the next hop. It does this because we configured R3 with a policy telling it to make itself the next hop for any routes it learns from R6. By default, R3 would actually advertise a next hop of 10.10.36.6, the router it learned about this prefix from. Now, if R1 thinks it can get to 69.69.69.0/24 nice via 3.3.3.3, but 3.3.3.3 isn't directly connected, then how does R1 get to 3.3.3.3? The answer is that we have to do a second lookup to find out how to get to R3's address. In other words, we have to resolve this next hop, and as it turns out, we know how to get to R3's address because of our IGP. Let's look at some of the extensive output on R1 for 69.69.69.0/24 nice. We actually see 2 next hops. The protocol next hop, i.e. the next hop that BGP is advertising, and the actual next hop, i.e. where the packet will physically go next. Show route 69.69.69.69 extensive. There he goes. Now he's got a 4th one, and you can do this because it will just look at the longest match of anything you specify here, which is with 3 octets. So far so good. We're running protocols, everything is being learned automatically, and everything goes into inet.0. It's a tradition as old as time itself. Now, in a moment, we'll make things spicy by turning on Mpls, because when we do, the story is a little bit different. But to understand why, we first need to make sure we're A-OK with the concept of a label switched path. Some quick revision. What is a label switched path? A label switched path, LSP, is a pre-agreed path between 2 routers in a network that a packet will traverse to get to its destination. The routers all communicate to indicate what label they'd like to receive for traffic destined along that path, and the connected routers will add that label to the packet before sending it. The receiving router strips the label and potentially puts a new label on it. A new label on as it forwards the packet on further down the path. Now, if you've never done Mpls before, you might think, why would you want this? Don't our routers already know how to forward a packet? Isn't that the whole point of a router? Well, for sure it is, but when we create label switched paths using Mpls, we get some super cool extra functionality beyond standard forwarding. For example, we can run layer 3 Mpls VPNs because suddenly we can forward by label instead of by IP address, which gives us the ability to have the same private IP address belong to multiple customers. We can perform traffic engineering where we create a path that goes a different way to what OSPF or ISIS tells us is the best path. We can automatically calculate backup paths that kick in immediately if there's a problem in the network. And a fictional 4th example, we can solve climate change. Wow, in that respect, think of an LDP not just as a path, but as a kind of tunnel. So I'm not sure how LSPs could resolve climate change. Maybe if the networking gear can work as a carbon what's the word? Carbon sequestration. Yeah, sequestration. If like Juniper gear can work as that, but even carbon sequestration has its limitations, and then when you sequester carbon, you actually get the carbon. So it's like if you just have a Juniper router in a head-end sequestering carbon, eventually the head-end will fill up with carbon bricks. I think carbon sequestration is actually a decent strategy, but it definitely has a lot of limitations. And not only that, in my opinion, the science really isn't there to just straight up sequester carbon. Like, we don't know how much carbon to sequester, we don't know where to sequester the carbon, because not all carbon is distributed equally, from what I understand. We don't know. Not only that, I guess there's aerosols in the atmosphere, which aerosols, hopefully everyone who has done their own research on coronavirus is really familiar with that term, because aerosols are just particles, things that just keep floating up and never hit back down. So there's a bunch of aerosols up in the air, especially at the really high levels. And from what I understand, if you just sequester carbon, you'll still have a warming effect because of the way those aerosols are affecting things. Like, it's just a really complicated problem with the worst imaginable consequences. I mean, imagine just not having air to breathe anymore. So I'm not sure if LDPs can fix that, so let's just move on without giving that any more thought. There's two ways we can create an MPLS label switch path. The easy way is to use LDP, or Label Distribution Protocol. By simply turning it on, our routers will form neighbor relationships with directly connected routers, just like an IGP does, and automatically start advertising labels. When you choose to use LDP, something interesting happens. Juniper routers only advertise labels for their loopback IP addresses. This means that if I turn on LDP in our example network, router 1 will learn a label to get to 3.3.3.3, but it won't learn a label to get to 10.10.23.0/24, the network connecting routers 2 and 3. There's a reason why it's only one loopback addresses. Why it's only loopback addresses. And we'll come back to that. Ooh, the suspense. LDP is very easy and quick to set up, but it doesn't give us much control. The traffic only follows the best path that we learned from our IGP. That's where our second method comes in, the resource reservation protocol. In Rsvp, we have to manually create all of our LSPs, specifying them by name on every single router in the network. The advantage, though, is that we get a ton of control over exactly what path our LSP takes. You can see here what a very simple Rsvp Lsp configuration looks like. Weirdly, it's configured under protocols Mpls, not protocols Rsvp. This is a bare bones configuration. So this is pretty much what I've got. All I've done is create the destination, but I could have done so much more. I could have forced the LSP to go via certain hops because he's using Rsvp. I could have told it to avoid certain links. I could have told it to signal a backup path.
to go a different way if the bandwidth goes too high, it's got a typo there, and tons more. Whether we choose to use LDP or Rsvp, the information about the LSPs are stored in one of two places, Mpls.0 or inet.3. We'll come back to Mpls.0 in a moment. For now, let's look at inet.3. Okay, so after all this reading, it actually might be normal that I only have MPLS, that I don't have an inet.3 table. I thought I would have it, but let's do a show route, and we'll see. I don't have an inet.3 table, but I do have an MPLS.0 table. That might be normal because I am using Rsvp and I'm not using LDP. A challenger appears, inet.3. If a router is acting as the ingress for an LSP, or to say it in English, if a router is the start of the tunnel where traffic enters or ingresses. Oh, that makes a lot of sense. Thank you. Okay. So, yeah, I had a lot of trouble understanding ingress because I was thinking of it from the point of the okay, the LSP. Thank you. What's his name again? Like David or something, or Chris? Yes, thank you. This guy. Your bad jokes were worth suffering through. Okay, so then you'll find the IP address of the other end of the LSP, the egress of the tunnel. Thank you for that. Oh my god, I can't thank you enough for that. In the inet.3 table. Let's look in the inet.3 table of router 1. I've turned on LDP on all interfaces in the routers, which means that I automatically have an LSP to the loopback of every router in my network. In addition, I've manually created one Rsvp Lsp directly to router 3. Let's take a look at what we see. So show route table inet.3. Now he does have something for Rsvp, which is surprising. So a few fun facts. First of all, notice that the only IPs we see in the table are the loopback addresses of our routers. Again, we'll come back to why this is. Ooh, isn't the suspense just killing you? Second, we see two entries for 3.3.3.3, the LDP signaled LSP and my manually created Rsvp path, which I cleverly called to in uppercase underscore uppercase ROUTER underscore 3. You can see from the asterisk sign that the Rsvp path is being chosen. Rsvp has a route preference of 7, whereas LDP has 9, so Rsvp paths will always get chosen over an LDP path by default. Third, on some of these routes we can actually see the exact label that will be pushed onto the packet as it goes out of the interface. The Rsvp route doesn't show a label for space reasons, but we could see this label if we added the extensive keyword. However, we don't see a label for 2.2.2.2 and 4.4.4.4. This is because these routers are directly connected to router 1. And by default, MPLS doesn't bother adding labels for packets destined to directly connected routers. You may have heard of this behavior before. It's called penultimate hop popping, PHP, and it's hands down my favorite phrase in the whole of IT. Penultimate hop popping. In fact, I fully plan to name my firstborn child Penultimate Hop Popping. I will do this regardless of how angry it makes my family, and no government in the world can stop. Did he do this? I mean, when was this? This was 2 years ago. He might have had a child, especially with. Did he actually? Does he have children now? He might have actually done that because this was written 2 years ago, so we might have a newborn baby under 3 years old named Penultimate Hop Popping, or Pen for short. But he would probably be called Pen by most people. All right, so. So it looks like I was actually almost done. Oh, okay, yeah. Anyway, PHP is generally a good thing. If you're the penultimate route in the LSP, you're doing a favor to the router acting as the egress of the LSP by popping the label before sending your packet. If there was a label, the egress router has to do twice the work because it has to look up the label, see the packet is destined for itself, pop the label, and then do a second lookup on the IP address. By using PHP, we're making things a bit more efficient. However, we can actually turn on labels everywhere with the explicit null command, as you can see below. When we turn this on, we see a label of 0 for packets destined to a router that is the egress for the LSP tunnel. This can be useful for a few things. For example, if you're carrying QoS information in the Mpls header, by keeping the Mpls header to the very end, QoS information can be carried all the way. So you've got to have this explicit null on there. Okay, so I think I'm going to stop here, and we're going to say next video. Okay. Alright, so that's gonna be it. Thanks for watching, and I'll see you in the next one.